Welcome. Today we'll explore how transformer models power intelligent chatbots, like the one you were probably chatting with today, right? Okay, so this is going to be a lecture that will be broken into few parts. The first part is going to talk about dataset, giving you a little bit idea of dataset. We're not going to do any data pre-processing at this stage. That will be followed in part 2 of the video. This lecture is mostly focused on the transformer architecture and how do you understand the transformer architecture and build a very basic transformer architecture which will work like a chatbot, will provide you the chatbot architecture that you can train your model or train your data on. Okay, so the beginning of this lecture, as I mentioned, we are going to talk about the data set. So the data that we are going to work with is called Cornell Movie Dialog Corpus. So if you just Google search this or just put it somewhere, it will just give you a lot of links and you can download the data. However, it's also provided in the GitHub link that I will be providing to the notebooks. Will also have all these links, so you can just download the data. So there's a file called movie underscore line dot text of the data set that has a structure like this. So line ID plus plus, then dollar sign plus plus. So this is basically a delimiter. Then character ID, movie ID, character name, and text of the utterance. So the line ID is just a line. Character ID, character also has ID. So this data set, I'll give more information on the data set in the next video, but this data set has a lot of movie dialogues actually that will help us in creating this chatbot basically. And then you have a movie ID, character name is Cameron, and text of utterance, so they do too. And then this is the next line. So you see the line ID number L1044, and the next one is L1045, and then it has a character with U0, then with the movie ID M0, Bianca, and they do not. So that's what it's like the utterance or the text or the conversation between Cameron and Bianca. Okay, so then you have a movie conversations.txt link from IDs from movie lines text to reconstruct the full conversation. So U0, that's the character. Then U2 is the character 2. M0. So this is the conversations that is happening between the character ID U0 and U2 in the movie M0, and these are the lines. So this is another txt file that has all these data, and you see so the u0 so u0 m0 Bianca, and can we make this quick? Roxanne, Karina, and are having an incredible horrendous public breakup on the quad again. So this is a conversation between Bianca and Cameron. As you can see, all these lines are again related to the line number from this line ID. Right? Okay, so that's kind of the giving you an idea of this movie conversation. So keeping this conversation in mind, which we will talk about in part 2, I want to now deep dive into an transformer architecture, which has an encoder and decoder part of the model, and which will actually help us in creating or learning these conversations between the characters. So the encoder part, you actually do a you give the conversation and you have to follow a few steps, and then in the decoder it's going to give you an answer, right? That's what a chatbot will do, right? Okay. So moving on, so what are transformers? So that transformers use word embeddings to convert words into numbers. So this is what we were discussing about our attention models. Then it will have a positional encoding to keep track of words. Transformers have self-attention that associate word similarity within input and output sequences. Encoder-decoder attention to keep track of things between the input and the output phrases and are not lost and which are not lost in transition. Okay. So, even though this is an example that's been given for a conversational chatbot, a more good example that you will be finding is, or a more generic example is text conversion, or language conversion. So, English to French or English to Spanish and things like that, right? So, this is where your encoder decoder attention becomes very significant. So in this transformer, if we move over to the transformer, you can see there are so in this example, I'm not going to talk about multi-head attention because we'll just stick to the basic three attentions that are being used in this transformer architecture. And I've picked some of the components of this, not all of the components of this. Okay. Um, so we'll have a self attention in the encoder. Then we have a encoder decoder attention over here, where the key and the values come from the encoder side, and the query values are from the decoder. And then finally we have a masked attention. So why masked attention? Because in the decoder part, which is basically used in most of this language models, the model has to train so that it cannot cheat, or it cannot know what is the next token. So it has to give a probability values based on which you get it will give you some token values, like, or the actual words that comes after something. Okay. Comes after, or in the translation, or in the chatbot, for example. Okay. So this is your basic part of the self attention. So we start with the self attention, then we move on to a residual uh, a residual layer, followed by residual layer, and then followed by encoder decoder attention, and then you also have a mask attention in the decoder part. So no matter how many words are input into the transformer, we reuse the same set of weights for self-attention, query, keys, and values. So when you are trying to train a model, the weights that will be given to the architecture is remains the same. Okay. Self-attention queries, keys, and values for all the words are calculated simultaneously. So that's one of the reason why you use transformer, is it can leverage the mechanism of parallel computation, right? So you can at the same time you can have matrix calculation happening in different GPUs, right? Okay. Because we can do all the computation at the same time, transformers can take advantage of parallel computation. That's what I was just mentioning. Okay, so then let's start with the self attention part of it. So here, pizza is awesome, great. So this is the sentence that is being that works as an input to my encoder part of the transformer. So we uh, need to have a way to convert these words into numbers, right? So that you can do further analysis or further calculations. So the two things that we have to work on is a word embedding and then a positional encoding. So in any of the situation, we do have to first use a word embedding, which actually converting words into numbers using word embeddings, and then also add positional encoding to understand the word order in a sentence. Okay. Okay. So finally, if you have a number of self-attention units together, you can use this multi-hit attentions. So if I go back to my transformer, while I didn't code, like for the next part, I'm not coding the multi-hit attention, but I'll definitely give you codes about how to, or ideas about how to convert this into multi-head. But in actual transformers, I believe there were eight multi-head, uh, but eight heads actually. I might be wrong. It's just a guess. Okay. Anyway, so mate multi-heads being said, you have, it will give you more relational information between Q, V, and K actually. So here it's converted into embedding, then here it's converted into positional encoding, and then finally we create three bits for query, value, and key. Okay. We take the positional. So now once we have done the positional encoding values and then pass them through self-attention values, we create residual connections and they make it easier to train complex neural networks. So the value from this positional encoding are added to this to the attention scores, or yeah, to the attention scores after it has passed to a self-attention layer. It allows the self-attention layer to establish relations among the words without preserving word embedding and positional encoding information. So this so you do, over here you don't have to keep a track of what was there for the positional and the uh, word embedding information, right? So it remains in this layer, and then when you add the residual connection back, then it adds it with your attention score. So it's just add backs to your attention scores. Okay. So these four features, just to reiterate again, word embedding, positional embedding, self-attention scores, and residual connection. These four features allow transformer to encode words into numbers, encode the positions of the words, encode the relationships amongst the word, and easily and quickly train it in parallel. So that's the uh, entire concept of a transformer, is to use multi-heads which can be trained in parallel in your GPUs, right? Okay, so now we will move into the decoder section. So as I am using this for a conversational chat, so let's just go back a little. So actor one, pizza is awesome, great. End of sentence or end of sequence. So this is what is passed into the encoder, and this is what I'm expecting to get an answer from decoder part. So that's really good. End of sentence. Okay. So the decoder part it's also built of word embedding, positional embedding. This has to be, sorry, this is mask attention scores, and then there's also residual connection. So instead of self, we are using a mask attention because we don't want the our transformers to cheat or a model to cheat. So we'll just mask the next token. Okay, so far we talked about how self-attention keep track of how words are related within a sentence. However, since we are creating a conversational chatbot, we need to keep track between input sequence and the output sentences, right? It is important for the decoder to keep track of significant words in the input. So the main idea of encoder-decoder attention is to keep track of the significant words in the input, and the relation between, to keep a track of the relation that is building up between the input and the output sequences. So let's take an example. We create two new values to represent the query EOS taken in the encoder. So let's now try to construct the encoder. So then we create keys for each word in the encoder. So we create two new values. So here in the this key query is coming from your decoder part, and we create keys for each word in the encoder. So there are four words, and we have a key value for all these words in the encoder section. Yeah, I'm sorry. All these words in the encoder section, and it also has it should have two values, but I just shown you just one example for each word here. So we calculate the similarities between EOS token in the decoder and each value of the word in the encoder by calculating the dot products. We then run the similarities to a softmax function. We then calculate values of each input word and scale those values by softmax percentages. Finally, add the pair of scaled values back to get encoder decoder attention. Okay. Okay. So let's see if I try to break this down. So here we have the encoder part, right? So pizza is awesome, great. And this is that is really good, end of sentence. And this is where I have my maxed attention, and this is my multi-health self-attention. And we create we have this query and values coming from your encoder part, and this key is created for each and every word in my decoder part. So bear in mind, all these decoder words are also transformed into numbers based on word embedding and positional embedding. And then we add another set of residual connection that allows the encoder decoder attention to focus on the relationships between the output and input. So this is the residual connection. So QKV, right? So this is my encoder decoder attention, and then that gives me two attention score values. And then finally we preserve the self attention, word encoding, and positional encoding. So we actually get the values from here and add it back, right? So here we do one layer of residual connection from the encoding of after before the words that were before using the mask self attention. This is from the layer that has the positional encoding, right? And add it back. And then this is after the encoder decoder attention, we also use a residual connection. Okay. Okay, so then we pass this to a feed forward. So finally, after we get the attention scores from the encoder decoder attention, we pass it to a feed forward network, and we get the softmax, which will give us probability values, and based on which we can construct the output, right? So finally, we need to connect a fully connected layer to calculate the probabilities of the tokens. That's really good end of sequence. The fully connected layer has one input for each value of the two current tokens, so in this case 2, and one output for each token in the output vocabulary, which is 4 in this case. So it's going to give me an output value based on the result here. because this is at the point of training on a, how do you train this model. So we are giving it the decoder value, and it has to give me the right values of the softmax probabilities. We ran the final softmax function to select the sentence that's really good, end of sentence. Okay. So this is in short how your encoder and decoder architecture will work for your chatbot model, okay, or a transformer model. So there's a lot of components, but in the next lecture, I'm going to mention a basic transformer without the multi-head concept, and I'm going to use a very simple demo at that point, or very simple demo data, and then followed by more robust transformer transformer exercise with this Cornell movie dataset. Thanks for listening and hope you like the video. If you like it, please like the video and also subscribe to the channel. Thank you. Hi, hello, welcome to our sessions on algorithms. Today I'm going to discuss about group anagrams, categorize string by count, and we'll be using arrays and hash maps to go to find the ultimate solution. So let's jump into the question. So this is of course a neat code or a lead code question. So I just copied the question from neat from lead code actually, and here's what the question says: given an array of string strs, group the anagrams together. You can return the answer in any order, so it doesn't look for any order. So input string eat, t, tan, 8, nat, bat, and then we are going to return it as bat, and then group nat and tan, and which is a list actually. So group this together and return it as a list, and then 8, eat, t, group these three words together and return it as a string. So what's the explanation? There is no string in strs that can be rearranged to form bat. The strings nat and tan are anagrams as they can be rearranged to form each other, right? So it has the same, it has three characters, and it's just arranged in such a way that it will form nat and tan. And then string 8, eat, and t are anagrams as they can be rearranged to form each other. And in example 2, even if you have a blank string, it should also return it as a list within a list. And then also, like, even if you have only one single character, it will return a as a list inside a list. So we have two ways to solve this problem. So I'll go over the solutions, but I'll only provide a solution for solution 2. But let's look at the solution 1. So solution 1, this is what we have to return, a list of list, eat, t, 8, tan, nat, bad, etc. So if we sort, eat becomes aet, t becomes aet. But if we sort each of the strings, the time complexity in this case becomes m star n log of n. So when we are doing a sorting, when we do a sort, usually the time complexity remains n log n. Okay. So where m is the number of words, so these are the number of words. So in this case, that would be around that's going to be 6, and average length of words, that's going to be 3, right? So we can do better. So if you are sorting it and then you are grouping it, that can be a solution, but we can do better with the time complexity. So let's look over here. So eat, t, 8, tan, nat, bat, so it remains the same. Now what we will do is we will use two steps. So one is create and count array. So count array will have a shape of or a length of 26. So what is it going to hold? So it's going to hold. So we are thinking that it's only going to be the string is only going to be characters between lowercase a to lowercase z. So that's the reason it will hold 26 26 or it is an array of 26, and use this count as a key to a hash map. So for example, if we have EAT, so EAT will have actually 1A. So there is 1 at the position. Actually at 0th position of the array, we will have 1. The others will be 0. Then again at the fourth position or fourth index, we will have E. And then at the 19th index, we will have D, and this will be similar for all these three words, right? So my key, if I use this count array as my key, so the key remains same for all these three words, right? So I can use this count key to a hash map, and I just keep incrementing the number of uh, or number of times or the number of words that have the same key, or I just use the value. So I keep appending the value, which is 8 eat, whenever I find the similar key, right? So so but we also have a limit. So it's not a log of n. So if I come to time complexity, so it has 26 characters. So each of these new count arrays will have 26 characters, and n is the average length of the word, which is 3 in this case. Then my overall time complexity is m star n star 26, right? So which is actually less than the previous solution of log n, right? So that's the reason we will go over and try to use the solution too. Okay. So let me start coding it. So class solution. Um, so def group anagram takes a list of string. So this what it says is list of string is et tan 8 nat bat etc, right? That's my input, and then returns a list of strings. So this is list and then string, grouping words that are anagrams of each other. So we are actually then kind of returning the words like this, right? So all these are grouped within a list. So we are actually returning a list of list. Okay. So now we are going to define a result. Res equals to a default dict as a list. So that being said, it is basically that I'm mapping character count to list of anagrams. Okay, so this is actually a dictionary. So this is a default dict of list, right? So it's going to hold a list. So each and every key is going to hold a list. Okay, so now we have to use two for loops. So S in strings. So strings is a list of string. Count equals to 0. So we are defining the length of the array. So it will have 0 with 26 characters. For C in S, count. So C in S, what does this mean? It's the character in your individual word. So S is now, for example, it will take E, A, T, right? So we are looking into E, A, and T as individual characters. So count ORD-C minus ORD-A plus equals to 1. So what does this mean? Okay. So ORD-C returns the ASCII value of character C. Okay. And ORDA is 97, ASCII value of character A. So if lowercase a has an ASCII value of 97, then my lowercase b will have an ASCII value of 98. So when I'm trying to form this array, right, of 26 of length 26. So at index position, so invariably A always becomes my index position 0, B becomes 1, C becomes 2, and things like that will move, right? So C minus ORDA gives the index from 0 to 25 for letters A to Z, right? So bear in mind C is actually a character, right? So count, uh, so the count plus equals to increases the count of the letter in the 26 length list, right? So if I have more than is more than two times, right? Then it will just keep incrementing the value, right? Or T or E or any other character for that matter. Okay, now let's understand the result. How are we going to what is this doing actually? So why we make it as tuple count, because when you have a key, it is immutable, right? So tuples are immutable, so it's better to convert this count, which is an array, into a tuple. So count is a list of length 26 where each index holds the count of a letter A to Z. Tuple count turns this list into a hashable key. List can be dict key, but tuples can. So list cannot be dictionary of keys, but tuples can be. Right? That's what I was kind of mentioning, that you cannot, it's immutable, right? It represents the signature of the words and how many times each letter appears. So again, taking T, count becomes 100. So this is at position 1. We have A at position index position 4. We have E, which becomes 1. Again, at index position 19, we have T. Right, similarly with ATE, count becomes this. So invariably your tuple of this array is actually the key, and this key is common to T and it. And then when the tuple becomes, or the key becomes common, then we can append the word, individual words itself, which is S in this case, right? So that will give me a list again. So that way I'm actually grouping everything together to a list. And then going to return the value of the result. I'm not going to return the key, but return the values of the result. So this is what we have. So from collection import default tick, from typing import list, and then that's the solution. And finally, if I use S equals to solution, a new solution, and then if I'm printing S group anagrams, and then I'm just passing this list, it will actually group together all the words that are anagrams of each other. Thanks for listening to the video. I hope you enjoy or learn. Actually, you should learn from this. And these are very important questions for your interview. Thank you.